Hello, and let's take a look at combining elements to form compounds. The difference between ionic and covalent compounds. So a compound, what's a compound, first of all? Elements combine together to form compounds. So we take two different elements off the periodic table and we stick them together chemically, that they're bonded together and they make something completely new. Like water is an example of a compound. Salt is an example of a compound that they take the elements and put them together and make something completely different. There's only two types of compounds. There's ionic and covalent compounds. Instead of all the world of chemistry, there's only two different types, ionic and covalent. Ionic compounds gain or lose electrons to become stable. Covalent compound is going to share electrons to become stable. So both of them have the goal of becoming stable. So ionic compounds are going to lose or are going to gain electrons, and covalents are going to share. So the atomic number is the number of protons and electrons. So we can assume in a neutral atom that the protons and the neutrons are going to be equal, that the positives and the negatives are going to equal each other out. So as we learned before, that the atomic number is the number of protons. An example, sodium is number 11 on the periodic table, so it has 11 protons and 11 electrons. So now that we know the number of electrons, that's really going to help us with how atoms bond together, because it's the electrons that really take part in it. The protons are nice, they're in the middle, but they can't really react with other elements. The electrons are on the outside, and so they're going to connect with other compounds, other elements to form compounds. So, 2, 8, and 8. We have 2 electrons go in the first shell, 8 in the second, and 8 in the third shell. So electron shells hold the electrons. It's kind of where they live. The first one can only hold 2. The next 2 can hold 8. So here we have that same sodium atom, and on the bottom we see that 2 electrons go in the first shell. So in that first orbit around, we're going to have 2 electrons, 8 in the next one. 8 plus 2 is 10, so that 11th electron is only 1 that ends up in the third shell. It's kind of like a cup instead of a bowl, instead of a large bowl. You can fill up the cup, it's going to overflow into the next bowl, and then anything left over is going to overflow into the large bowl outside. Okay? So we can fit all of our electrons in the first 18 elements just in these first 3 shells. And that's why we're going to simplify it. We're going to look at just these 18 elements. So here we have the octet rule. 8 is great. Elements want to fill the outer shell to be happy. So whatever the last shell in that element, it wants to have a complete octet, 8 in that shell. Hydrogen's the only one that needs 1 electron to be happy, since the first shell can only hold 2. Okay, so hydrogen has 1 electron, and it wants to have 2 to have a full outer shell. So we call it the octet rule, but hydrogen is an exception to the rule. All other elements on the periodic table want to have 8 electrons total. They feel complete and balanced and stable and enjoy long walks on the beach together. They are completely complete. Elements will gain, lose, or share electrons to obtain the octet. So by these 3 different ways, they can get that octet. Noble gases already have 8, and they're happy all by themselves. These are the bachelors of the periodic table, and it's not going to combine with anything else. That they already have their 8, and they don't need to gain, lose, or share electrons with another element to be happy. So, how do we keep track of electrons? Atoms in the same column have the same valence or outer electrons. Word we're going to use is the valence electrons, which just means the outside, the last orbit, how many electrons are in the outside. It's found by looking up the group numbers on the periodic table. The vertical columns on the periodic table are called groups. Group 2A, or Roman numeral 2A, the beryllium, magnesium, calcium, etc., these ones have 2 electrons. So group 2 has 2 electrons. Go by the Roman numeral, it's going to help. Okay, so the outside electrons determine how many atoms will bond. So here we have groups 1, 2, the 1A, 2A, 3A, 4A. Go with the Roman numerals, and that's going to help you to figure this out. So that's how many electrons in the outer shells. We squished the periodic table down to the first 18 elements to keep things simple for sure. Okay, so these are the outside electrons. So if we looked at the noble gases all the way on the right, those have 8 electrons in its outer shell. That's what makes them happy. So an ionic compound is either going to lend or borrow electrons. We go by the rule of opposites attract, that the positive, or ones that have ones to give are going to give them away. Ones that need one or two are going to gain electrons. So metals and nonmetals. This is another big important difference between metals and nonmetals. That metals are going to form a positive ion, and nonmetals form negative ions. So you can see from the little diagram here, we have sodium chloride making table salt. So sodium has 1 electron in its outer shell. It's from the group 1A elements. And chlorine isn't from the group 7 elements. And so chlorine has 7, it wants 8. Sodium has 1, and it wants to get rid of that 1, so its next layer has 8 in it. Okay, so sodium is going to give an extra electron to chlorine. Chlorine is going to have a full octet, and then the opposites attract. So sodium loses an electron and becomes positively charged.
Could I have a custodian to the adult ed office or dial 9529? Could I have a
Just like in
custodian
class,
to
we
the
get
adult
interrupted
ed
by
office or dial 9529?
announcements. Excellent. So that's how then these two elements have opposite charges. The positive and the negative attract each other. So ionic bonding. There's 3 little mini steps that go in there for the sodium to be attracted to the chlorine. So first, the sodium has to lose an electron. The second step, chlorine's going to gain that extra electron. Now that they have a charge, the positive and the negative are going to attract. So sodium takes on a positive charge because it has 11 protons and 11 electrons. If it loses an electron, the protons are going to be winning, and it's going to have a +1 charge. Chlorine is going to gain an electron. Electrons are negative, so it's going to have a -1 charge. Now the two opposites attract. Metals lend, nonmetals borrow electrons. Okay, so the outside electrons determine how an atom will bond. Okay, so the metals are going to be in orange here. Those are all metals, and they're going to get rid of an electron, and the nonmetals are going to borrow electrons. Okay, so for example, the halogens, fluorine and chlorine, the second to last column over on the right-hand side, they have 7 electrons. It's going to borrow 1 electron. Okay, because it takes less energy to borrow 1 than to give away 7. Okay, the ones on the left, lithium, sodium, potassium, those ones have 1 electron, and so they're going to lend those away, so it gets rid of that outer shell with less than 4 electrons. So it's going to give it away. It's going to be less energy to give away the 1 or 2 electrons and gain 6 or 7. Okay, so characteristics of an ionic compound. There are several assignments within the unit that we're doing, comparing the two. It's important to know the difference. So what's an ionic compound like? It dissolves easily in water. Salt dissolves easily in water. They have a positive and negative end, so polar water will dissolve it quite easily. There's an animation here, which we can look at later. In solution, they conduct electricity. If I dissolve salt in water, salt is the classic ionic compound that we have familiarity with. So if I dissolve salt in water, it's going to conduct electricity better. It's a crystalline solid, so it has a definite shape to it. It forms a repeating pattern of positive and negative ions. And it has a high melting point. So here's some regular crystalline solids that we call ionic compounds. So we have calcium fluoride, zinc sulfide, and so on. You can see that there are these crystal lattices of repeating patterns that they're going to exhibit. Okay, so it's not just one Na and one Cl to make up sodium chloride. It's a repeating pattern of an Na, then a Cl, then an Na, then a Cl. Okay, so here we're looking at a 2-dimension. The formula for sodium chloride is 1 Na and 1 Cl. So really it's 1 to 1. They're each stacked against each other, but then you have another Na right after it, then another chlorine after it. You can go vertically. In all 3 dimensions, these atoms are stacked together. Okay, same thing with calcium chloride, even though calcium is CaCl2. So there's 2 chlorines for each calcium, and those are all stacked together in a repeating pattern over and over and over again. They kind of look like floor tiles or wallpaper, these patterns that go over and over again. Okay, covalent bonding. The second type of bonding is covalent bonding. So here we have methane, which is 1 carbon with 4 hydrogens stuck to it. And you can see the electrons in between, represented by the blue and red dots, that they're being shared. One's not giving it away, one's not taking, but they're sharing it together. So carbon has 4 electrons. We say those are the blue ones, and each hydrogen has 1 electron. So the hydrogen gives in a sharing relationship, and then the carbon gives back. Okay, so they share their electrons. So the carbon has its 1, 2, 3, 4, 5, 6, 7, 8 electrons to make it happy. And hydrogen gets its 2 electrons to make it happy. Remembering that hydrogen is the exception to the octet rule, that it just wants to have 2 to be happy. Okay. A metal and a nonmetal are stuck together. If we transfer electrons from one to another, we're going to have an ionic bond. If we take 2 metals, they're just going to mix together. They're not going to react, and we have an alloy. If I have 2 nonmetals, okay, so if I take a metal and a nonmetal, we're going to make an ionic bond. 2 metals don't make anything. They just melt together and make an alloy, like brass or bronze. And if we have 2 nonmetals, then neither one's going to give away its electrons. So they're both in an ionic compound. They're the ones who gain electrons. So neither one's going to give away their electrons. So they have to share. This is going to be a covalent bond. So you can tell it's a covalent bond if there are 2 nonmetals. There aren't that many nonmetals on the periodic table. And so just with these elements, no metals are involved. The way we can set up covalent bonds is through electron dot diagrams, or Lewis structures. So electron dot is just going to be that one element. So you write the symbol of that element. We're using, for an example, element X, which is just a variable for any element. There's no element X. Put 1 dot for each valence electron. So you look at the group it's in and figure out how many electrons in your outer shell, how many valence electrons, and you put 1 dot for each one. They don't pair up unless they have to, and then 2 dots for each side, for the top, the bottom, the left, and the right. So it kind of makes a square around the symbol. So if we're going to do electron dot diagram for nitrogen, nitrogen has 5 valence electrons. First, we have to write the symbol. So the symbol for nitrogen, N. Then we add 1 electron to each side. Nitrogen has 5 valence electrons. It's in the group 5 elements. So we put 1 up top. Don't pair them up, so we're going to go around nitrogen with 1 each. And then finally, it's going to be forced to pair up. And we're going to pair that 5th electron on top. So that's the electron dot diagram for those elements. For practice, you can look these ones up. Oops, I'll go back. Thought there was one more. Okay, so sodium, we looked that up on the periodic table, and we're going to figure out that it has 1 electron. We just draw 1 dot on its side. Magnesium has 2 dots. We draw 2 dots around it. 1 maybe on the top, 1 on the left. Carbon is going to have 4 electrons. They're not going to be paired up. It's going to be 1 on each side, 1 on the top, 1 on the left, 1 on the right, 1 on the bottom. Oxygen is going to have 6 electrons, so we'll have 2 lone pairs and 2 unpaired up electrons on 2 sides. Fluorine has 7, draw 7 dots. Neon is a noble gas, so it's going to have the full octet of 8 all the way around. Helium is in the noble gases, but it only has 2 electrons to put around it. Even though it's in the group 8 noble gases, it's still, remember, we have the 288, where the first shell only has 2 electrons in it. Lewis structures. Useful way to visualize valence electrons. The dots represent the number and the placement. Okay? So if we had 2 fluorines, each fluorine has 7 electrons, so we draw the dots around. The second atom also has 7. If we share electrons, both are going to have full orbitals. Okay, so those 2 in the middle are shared between them. If we count all the way around fluorine on the right, it has 8 valence electrons. If we count the fluorine on the left, it also has 8 valence electrons. Okay, so both are happy. So fluorine is diatomic. It's never alone. It uses the buddy system. Each fluorine atom is going to be buddied up with another fluorine. Okay, so here's another example. Fluorine has 7. Okay, it's going to make a compound with nitrogen. Nitrogen has 5 around it, so there's 2 paired up electrons on the top of nitrogen, and then on the left, right, and bottom, it's just a single electron. So it has rooms, just kind of like Legos are going to snap together, that these elements are going to fit together, and they're going to make complete sets of 8. And so every element is happy. So here's an example of water, a very common example that we should all be familiar with. Hydrogen, each hydrogen has 1 valence electron, and it wants 1 more to be happy. Oxygen has 6 valence electrons, and it's going to want 2 more. So it's got gaps to fit 2 more electrons. 6 plus 2 is 8. They're going to share together to make each other happy. So one hydrogen is going to go, let's put it on the left here. There's that gap in the complete octet for 1 more to go in on the left. So we're going to stick 1 hydrogen there. We're going to put the pieces together.